Hello everybody and welcome back. Root Beer here. We're on to the last question of the year 2000 Fermat paper. So, amongst all the multiple choice contests from the year 2000, this should be the hardest question, and hopefully you guys have had a chance to take a look. Maybe we'll get the same answer. Who knows? I haven't even done the question yet, but let's take a look now, and we'll see what we can see. Alright, so question number 25. The given cube is cut into 4 pieces by 2 planes. Okay. The first plane is parallel to face A, B, C, D, so it's going to cut somewhere, but it's going to sort of be parallel to the floor, and passes through the midpoint of edge BG. Okay, so it's going to slice the cube right in half. Okay, it's going to go through this midpoint, midpoint of CH, midpoint of DE, and the midpoint of EF. The second plane passes through the midpoints of edges AB, AD, HE, and GH. Determine the ratio of volumes of the smallest and largest of the 4 pieces. Okay. So, geometry in 3 dimensions is usually a very tricky thing for people. Especially on a contest like this, where we just have a very flat picture and it's very hard to tell what's going on. So you may have heard me in sort of other videos recommend, oh, well, you can bring a pair of dice and things like that, and it's always good to do that. Obviously, if you have a very particular proctor in your room, you may be asked to remove said items, but a pair of scissors is pretty good. If you can get an analog wristwatch, just to remind you counterclockwise and clockwise. Both kinds of compass can be good, the one northeast, southwest, and of course the one to draw a circle. And if you can, occasionally the basic geometric shapes, the basic 3-dimensional geometric shapes are good. You can pick up like a wood set from a craft store with a small wooden sphere or a wooden triangle and stuff like that. And they're very plain, so I don't expect someone to say, oh, you're smuggling in notes. So with a question like this, when it involves a 3-dimensional cube, if you have a cube handy, so I can just use one of the Rubik's Cubes I keep in the office, it's a good idea to have them, because now I can sort of pinpoint and visualize things about this cube that I maybe otherwise couldn't with a 2-dimensional picture, certainly not the one they provide. But I can sort of see, okay, well, the first plane's going to cut it exactly in half, and then the second plane's going to come down at such an angle that it hits the 2 midpoints, and then it exits the 2 midpoints. And I see that that's very symmetrical. Both cuts would split the cube into 2 equal halves. So by symmetry, I think we could make the argument that of these 4 pieces, 2 of them are going to be the same size and they'll be the smallest piece, and 2 of them will be the same size and they'll be the largest piece. So we're sort of just figuring out the ratio of one piece to another piece, as long as they're not the same piece. But if you don't have 3-dimensional props, that is okay. Doing questions like these and getting good with drawing appropriate diagrams and trying to perceive what you have on your piece of paper in a 3-dimensional way, that's excellent practice for these contests. So how about instead of, I put down the Rubik's Cube, instead of just holding that up and saying, oh, look at this, let's draw a picture as one might would on a contest. Okay? So we have A, B, C, D. Let's go right to our notes. And I'm going to, I like drawing a big picture if I can, so maybe this will take up the whole page. Let's draw a cube the way I know how to draw a cube. So the way I prefer to draw a cube is I start with the front square. And then I just make a copy of this translated back a fair bit. So I want this point to go here. I think that's a little too wide. And then I connect up corresponding corresponding points. Okay, so I have my cube. And let's label it, I think B was over here. Let's just double check. A, B, C, D, okay. They're going around in a counterclockwise manner, that's fine. Usually they go clockwise. Alright, A, B, C, D, and it was B, G, right? D, so this will be E. Well, one of these will be F. I'll say this is F. No, this has got to be H. This is F. So with my big picture, I will label exactly the points that they're talking about. So the first plane passes through the midpoint of BG, and it's parallel to ABCD. So as I already said, it's going to cut through all the other midpoints, and it's going to basically cut this whole thing in half. Okay. So that's the blue plane, the first plane that cuts it sort of in half into two smaller rectangular prisms. And now the other one. And what does it say exactly? Midpoints of AB, AD, HE, and GH. AB, AD, HE, GH. So we can see these points here are sort of opposite each other. And so what's going to happen is it's not just going to cut in a rectangle. It's actually going to sort of, and this is part of the problem with this question. What makes it so hard is we have to sort of figure out how exactly is everything being cut. Okay, and that's where having a Rubik's Cube or having just a cube that, a small wooden cube that you could draw on with a pencil, I think that would be fantastic. So, what do we think is going on here? Basically want to cut that out and then I want to fill it out. So I think we're going to get sort of a hexagon-like shape. And so it's also going to intersect this, the midpoints here and here, the midpoints of BG and DE. And we're going to get this sort of hexagon pattern cut out. Okay. And so I will use in green to trace out the smaller area. So from what I can see, the way that this is cutting, because the midpoint of AD is directly opposite the midpoint of GH, and same with HE and AB, we have four pieces here. So we have one big one at the top in the foreground, and a smaller one in the back, and we have a smaller one in the front, although flipped over, and a bigger one in the back in this bottom half. I say that the smaller pieces by symmetry are the same size, and the bigger pieces by symmetry are going to also be the same size. So that lets me make things a little easier. Now I just need to figure out the area of this green piece, which I will trace. Oh, that's awful. So the question is, where does the red plane cut the blue plane? What am I at a terrible angle here? What is this? So actually, we also need to label where the red plane crosses. But since the red plane hits the blue plane at these 2 points, and they're not parallel, they're not coincident, these planes will have to intersect in a straight line. The red plane intersects the blue plane at this diagonal between these two midpoints. And so using that, we can sort of finish up what we say is the green figure. So this green one is what we claim is the smaller figure. and we'll use yellow for the bigger figure. Now, I could label the yellow one on the top, and I think that's certainly an excellent way to go about it. But what I'm going to do is I'm actually going to label the yellow piece on the bottom, because I think we can get a bigger piece just by considering. We can get a bigger object that's easier to understand if we don't keep them side by side in the top, if we keep them one on top of one another. And I'll show you what I mean in a moment. So, what we have is sort of, oh yes, I need to put the green and yellow lines together. So we have the yellow piece sitting underneath the green piece. But I've done that so we can easily perceive it, and because I think we're going to get a bigger structure like a tetrahedron. So, I could label the yellow piece up here, but then we might have trouble with our depth perception seeing what's the green piece and what's the yellow piece. So, if we are looking at this cube sort of head-on from the point C, the green part is in the top and at the back, and the yellow part is the bigger piece. It's in the bottom at the back. From CH being sort of our center line. Okay, so if we wanted to go back to our cube, if you're looking at it head on, the top at the back here, this corner up here, is sort of where the green piece is going to lie, and then here at the bottom, at the very back, is where we perceive the yellow piece, so the bottom at the back here. That's just the idea. Okay. So, this green piece is sort of, it's got a triangular base, and it's got a triangular top. It's sort of as though it's been truncated, a little piece has been cut off. And in the same way, we see that the yellow piece has a triangular top, very similar. And it's sort of got little triangle, it sort of smooshes up against the sides of the cube as though we wanted to spill out and complete this triangle, just like we might want to complete this triangle right here. So, what we want is the ratio of the green piece to the yellow piece. Okay, that's what we're looking for. So what I'm going to do is I'm actually going to say, you know what, this front piece, it's actually really messing up with my depth perception. Same with this front piece on the bottom. This copy of the smaller piece and this copy of the bigger piece, they got to go. And what I see is, if I were to add in some triangles here, sort of extend FG and FE, so let's just extend FE, FG, and FA. Draw this a little bigger. Alright, so the green piece sort of looks like this. And the yellow piece sort of looks like this. So this is roughly what they look like. Okay, sitting one on top of each other with the other pieces removed. Now, especially this top part, it looks like the bottom half of a tetrahedron. So, what if I were to draw that in? Now I have a tetrahedron. And if I were to extend this line down here, and this looks very similar to this diagonal, which stretches all across. What if I were to complete that up? Suddenly I have a nice big blue tetrahedron with some smaller tetrahedrons removed. Okay? It's almost as though I took an even bigger cube and lopped off most of the sides. I get a nice right-angled, so the angles come to a nice right angle. It's not necessarily one of those, it's definitely not a regular tetrahedron that you might be familiar with. It is a right angle or orthogonal tetrahedron. Okay? And what we've done is we've cut off some smaller orthogonal tetrahedrons. So, does this in any way help us? Well, I would say yes. Okay, and here is my reasoning. Let's get some numbers on here. Now, I have no idea what the side length of my cube is, but I do know it's a cube. So if I say this length is x, and this is x, then this is x, then this is x, everything basically is x. And I do know that the midpoints of AB and AD are used to help construct this guy. So I know that this length is a half x, and this length is a half x. Okay. I know this length down here, g to the midpoint of GH, that's a half x. 1/2 x. I know that this length here is a full x. A full x. This is a half x. This is a half x, sort of the spine of the green piece. And the spine of the yellow piece. Those are both a half x. Okay. This is a half x, and this is 1/2 x. Okay. So I've got some actual numbers here. And this length here is an x, and this is an x. So if I want to sort of complete this triangle here, if I go, what is this height here? Let's call it y. Okay? And we'll look at this side triangle right here. I have x, and then a little bit up, I have a half x, I have a y, and I have a 1/2 x. I have some right angles in here. These guys are going to be similar triangles because these two lines are parallel, because our blue plane cut parallel to ABCD. So these are going to be parallel, and we do get a similar triangle. So that means that x over 1/2 x, so these two bases are in the same ratio as the two heights. So that's going to be 1/2 x plus y over y. Okay? And when we work all that out, don't worry, we will be coming back to the picture. That first ratio turned out to be 2. So 2 is the same as 1/2 x plus y over y. And we can work this out and show that y is going to have to be 1/2 x. Okay? So once we know that, we can say not that that's y, but that that's 1/2 x. Okay? And by the same reasoning, the same exact reasoning, we're going to get that this is 1/2 x and this is 1/2 x. If you wanted to, if this were a written style question, maybe this is a Hypatia question instead, we would need to probably justify why each of these lengths is also a half x. But I'm telling you, it's the exact same calculation. And now we know the dimensions of this tetrahedron. Okay, so let's sort of redraw the picture, because we're going to be working over in this space a little bit more now. So we get sort of a right-angled tetrahedron, and its side lengths are 3/2 x. Okay. And what do? Well, we chop off a top little bit. We go down about 1/2 x and we chop it off. And then we go down another 1/2 x. And cut there. And then we cut along the sides here at a 1/2 x and 1/2 x. Okay, and this smaller portion in here is going to be the yellow thing that we want. So this is yellow in here. And in here, we sort of have the green portion that we want. Okay, so knowing that we have cut the triangle into sort of thirds almost, it can really help us figure out the ratios here. And we got to remember, our ultimate goal is figure out the ratio of the volume of the yellow piece to the volume of the triangular piece. Now, each of these smaller tetrahedrons they're congruent. And they're also similar to the big tetrahedron. Right? The big tetrahedron has it's right-angled, sort of. It's orthogonal. It meets at a distinct cube corner. And it's 3.5 x, 3.5 x, and 3.5 x. Well, each of these smaller ones is right-angled. And the lengths that meet at a right angle are 1/2 x, 1/2 x, and 1/2 x. So the ratio of their side length to the big side length, so the side length ratio of 1 to 3. Okay. Now, when you have, if we stop and we think about a triangle, just a regular triangle, and if it's got side length S and area A, and we double this triangle, we make it similar, but we double it, then what happens is we get 4 times the area, because 2 squared. Area is a 2-dimensional property. Length is a 1-dimensional property. So 2 to the power of 1 times S equates to 2 to the power of 2 times the area. And when we do volume, we have a side length of S, and we make the whole thing bigger, 2S. The volume, if it was V, we would get a volume of 2 cubed. Or 8. So what you need to do is when you stretch by a common factor and you want to see how the area is affected, you square that common factor. If you want to see how the volume is affected, you cube it. So to get from these smaller tetrahedra to this big tetrahedron, we stretch them by a factor of 3. So the volume volumes between the two have a ratio. Why do I always write ration? So the volumes have a ratio of 1 to 3 cubed. 3 being the ratio, they have 1 to 3, but we cube it because we're in 3 dimensions. So that's 1 to 27. So each of these smaller tetrahedra is 1/27th of the bigger one. So the combined area between the green piece and the yellow piece is 27 minus 3, so it's going to be 24 of the total area. Of the total volume of the tetrahedron. Okay. Now notice that the green piece is contained in its own smaller version of the big tetrahedron. And that's what we're going to look at right now. All right, so we have this piece right here, which is 1/27th of the total volume of the big tetrahedron. But how about this tetrahedron? Well, it's got a side length of x. So the ratio of its side length to the big tetrahedron is x to 3/2 x, or rather 1 to 3/2. Okay, fantastic. So, the volumes have a ratio of 2 cubed to 3 cubed, because it's 1 to 3/2 is the same as a ratio of 2 to 3. So 3 cubed, or 2 cubed to 3 cubed, 8 to 27. So the green piece, which is this stuff in here, is well, the tetrahedron it's contained in is 8 copies of the small tetrahedron minus this top copy, so the green piece is the same as 7 copies of the very small tetrahedron. Okay. Now, if we take a look at the big picture, we get that the yellow piece and green piece well, overall the big tetrahedron was 27 small tetrahedrons, and then we subtract off 1, 2, 3. So together the yellow and green account for 24 small tetrahedra. Okay, and we know what the green one is. The green one is 7 small tetrahedron. So the yellow piece is 24 minus the 7 for the green piece, which is 17. And so now we know the ratio of the green to the yellow. The green is 7 small tetrahedron, and the yellow is 17. So we get a ratio of 7 to 17, and I think that was one of the answers. Was it B? No, it was D. Okay. So it took us a while to get there, and rightfully so. It is the last question on the Fermat. But certainly this really shows that three-dimensional geometric questions can be very difficult to get your head around. I mean, we had to first figure out which pieces we were talking about. Fortunately, the symmetry of the situation easily singled them out for us. And then we really had to use some spatial reasoning and fill in the blanks and say, hey, this is a larger chunk of a big tetrahedron. Now, I don't know if that's the way they did it online, because you can look at their solutions online. But this is certainly the thing that jumps out at me because of these triangle pieces that are basically, they scream something is missing. They scream complete this line up here, please. And so once we have that tetrahedron, then it becomes a question of figuring out ratios, understanding how side lengths affect volumes, and then ultimately isolating for one of them the green, and then we get the green and the yellow. Not an easy question. No, 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 no. But a good one to illustrate how difficult three-dimensional problems can be, and an excellent one to practice because it is not at all intuitive that you need to create that bigger tetrahedron. But I would say once you do it, things come out a little more easily. I honestly can't think of any way off the top of my head to do this question without considering the bigger tetrahedron. So this does seem like a very challenging question. And as I said, rightfully so. So I think it's in a good place, and overall I would rate this contest very highly. And I think that's it. I think we're done with the 2000 Fermat paper, so I guess it's on to the 2001 paper. But of course, we'll have to do that in another video. So thank you guys so much for watching, and of course, I will see you all next time.